one of the things that we need to learn, especially if we're moving into the field of AI, we've got enough applications capabilities underneath us, but we're somewhat lacking in the fundamentals, and we know it. And every time we pick up one of those classic papers like, Hinton, LeCun, Andy Nings, any of those top heavy hitters who've done the real fundamental work. But the point is, they've set the fundamentals. So the question that we have is, what are the fundamentals? What do we absolutely have to have? Maybe not completely mastered, but at least under our belts a little bit. And let me just show you this book. It is Statistical Mechanics. I will get you a screenshot of the close-up on this later. Statistical Mechanics, a set of lectures by Richard Feynman. And Feynman is, oh God, he is so one of the classic greats of the physics world. He is known for being not only a great theoretician, and he evolved several very important and useful methods, one of which is truly crucial in variational inference, which is the leading machine learning method right now. But he's also extremely well known for being a lucid and engaging and very clear protagonist and expositor of physics methods. So you might think, okay, I'm going to sit myself down. I will devote the next several months of study to statistical mechanics, and I'm going to go get a textbook and, what's highly recommended. And you suppose that you managed to get your hands on this one. Let's just take a look at the table of contents together, okay? Now, I personally would find this a good read, but that's me. So here, I'm just picking this at random. Chapter 5, Order-Disorder Theory. Now, I personally think that that's important, but it might not be needed for what we're doing right now. Chapter 6, Creation and Annihilation Operators. And so we have things like an anharmonic oscillator, systems of harmonic oscillators, phonons, field quantization. Chapter 7, I'm skipping a bunch of things, spin waves, oh my God. Chapter 8, the Polaron problem, oh my God, look, darlings, I love this kind of thing, but you do not need this. It's way more than you need to be able to get into the physics that you need for AI. Specifically, the physics that you need for energy-based systems. Statistical mechanics. Now, the basic underlying idea there is that you can do at this very microscopic level some investigations into how particles in a box, so to speak, behave. What we're interested in is the notion of how it is that you can describe these particles in the box as a metaphor, okay? As a metaphor for the energy-based systems that comprise the entire range of things that form deep learning in GANs. That means we're starting with a Hopfield, then the Boltzmann machine, then the restricted Boltzmann machine, then the deep learning, and then we get to GANs, and then whatever builds on that. And CNNs use the methods. All of these advanced layered neural networks use these methods. So you can't get into that literature without a little bit of the stat mech, because you need that vocabulary. Now the question is, how much stat mech is enough? Because unless this is particularly your thing, you don't want to spend, your holiday or even the next year reading that kind of thing. So here's what you need. 3 concepts. You need something called microstates, never mentioned in the neural networks AI literature, because it's fundamental at such a level that you deal pragmatically with the next 2 concepts. But if you study it enough so that you wrap your head around it, then you understand how these next concepts fit into place, and you're just a little bit more secure. So, microstates. Then the partition function based on microstates. Then the notion of free energy at this statistical mechanics level where you're dealing with many, many, many little particles, each of which has an energy state. Once you've done that, microstates, partition function, free energy also including entropy, so anything that you've ever heard about entropy gets folded into that. Then you write that out in the simplest possible statistical mechanics equation called the Ising equation, or the Ising model. And this is what's used as the metaphor for building your neural network, for building your Boltzmann machine or your Hopfield or whatever, and then whatever construct you build that is based on that. It's really not that bad. You just need that amount. You don't need the whole book. You need a few small things. We do have a solution to this little dilemma. It's a 3-week short course in the top 10 terms in statistical physics. We're offering it through Themesis. Please check out the link in the description box. That will take you right there. You'll get an immediate PDF on the top 10 terms, of course. And reading that within just 1 hour, you'll immediately feel much more comfortable and at ease when you go back to one of the classic neural network papers. However, you're going to get, over the next 3 weeks, for 5 days out of each week, an email with a little bit of a video, a little bit of supplemental material, and just something to coach you along your way and keep you enthralled, amused, and entertained. And on the last of the 5 days for each week, we give you a little self-check, something that you can do to go back to some of the source and realize, wow, I really do understand this more. So check out the link description box below. We're looking forward to seeing you there. Have a lovely day.